Okay, welcome back everyone to the morning session. So we're happy to have José Figueroa-O'Farrill from the University of Edinburgh, who's going to talk about Lie superalgebra deformations and D11 supergravity backgrounds. Please, José.
Okay, this is fine, speaking on that? Yes. So thank you very much for the invitation, Hisham. It's a real pleasure to be here. First time in the Emirates. Looks a lot like the part of Spain where my mother lives, actually, all the palm trees. It kind of feels like home. Anyway, right. So I wanted to tell you about some joint work that I've been doing with Andrea Santi, and also I'll mention some results of Andrea on his own, which I think are very interesting and very recent, about the sort of a new algebraic representation theoretic approach to the classification problem of supersymmetric supergravity backgrounds. So let me set up some notation, tell you what's known about this, and then tell you a little bit about the approach. And please interrupt any moment. I think just press the button and ask questions. And I hope this works. Okay, so let me set the notation. So it's kind of difficult to write, 110 every time. So I'm just gonna use notation. So V is going to be 11-dimensional Lorentzian manifold, and eta is going to be the metric. So 11-dimensional not manifold, vector space, Lorentzian vector space. So it's kind of the model. So associated to a vector space with an inner product, of course, you have the Clifford algebra. And inside there, the Lie algebra, well, the spin group itself, but in particular, the I'm going to use a notation S for the one of the two irreducible Clifford modules. So this is 32-dimensional, as we all know. It's real, and it's symplectic. So it has a symplectic structure, which I'm going to call omega. I'm going to use it only once. And it obeys the following property. It obeys that omega of S1 and then Clifford action by a vector on S2 is negative. Okay. So the transpose of Clifford multiplication relative to the inner product that I have on, I think I can do this. I can, does it? No, maybe not. Does it do that? Okay, very good. So, okay, so I have an inner product on V, and I have an inner product, although symplectic, on S. So the transpose of Clifford multiplication gives me a map, which is called normally the Dirac current. Let me call it kappa for. So this is symmetric bilinear in this case, from the spin representation to B. So how is that defined? So if I take the inner product of K of, let's say, S1, S2 with any vector, what I get is the symplectic inner product between, let's say, S1 and then VS2. And it follows from the fact that omega is symplectic, and because of that minus sign here, that this is actually a symmetric. This is symmetric. So kappa S1, S2 is S2, S1. So in old language, kappa of S1, S2, this is what we would normally call S1. So the muth component of that is gamma mu S2 or something like that. C being the charge conjugation matrix, which is a symplectic structure in this case. Okay, so the only reason I mention this is because that is the map that goes into the definition of the Poincaré superalgebra. So let me just set the notation. So P is going to be, for me, the Poincaré superalgebra. It's a Z-graded Lie superalgebra. So it has concentrated in 3 degrees. So P0 is going to be SOV. In -1, I have the spinor module, and -2, I have the vector module. So this is Z-graded Lie superalgebra. The origins of 11 dimensions supergravity, as Mike pointed out in his video, is the result of NAM. So this is NAM in 1978, that basically said that the smallest irreducible unitary representation of the Poincare superalgebra, this one in 11 dimensions, is induced from a representation of the little group. So this is massless representation. So the little group is SO9. So let's say smallest massless unitary irreducible representation is induced from the following. So it's induced from symmetric traceless tensor. Okay, so W is the vector of SO9, and sigma is the spinor of SO9. So it's going to be symmetric traceless, the symmetric traceless of the vector representation, the gamma traceless spin vectors, and then the three forms. And so it's induced from this representation, and this is SO9, which is the so-called little group. So in physics, we immediately recognize, we know what these representations correspond to in terms of fields. So the first summand is symmetric, this one is a gravitino, and this one is a three-form potential. Okay, so NAM conjectured that there should be a supergravity theory, right? You have a metric, you have a gravitino, and then this three-form potential. There should be a supergravity theory in 11 dimensions with that field content. And this was constructed by Kremer, Julia Scherk. Later, 78. And basically, this gave rise to what we now call as 11-dimensional supergravity. Anyway, I'm not going to necessarily write the theory down, but let me tell you what the geometric data that goes in specifying a solution of 11-dimensional supergravity. So there is a Lorentzian 11-dimensional manifold, which is also a spin, although one can perhaps relax that slightly. But anyway, so there's a spinor bundle, which I'm going to call $sign. As my friend David Calderbank says, there's big money in spin geometry. So that's why he calls it $sign. And there's a four-form, which is the field strength of that three-form potential that Nam discussed. And it's closed in the case of 11-dimensional supergravity. And perhaps the most important piece of data here is the fact that there is a connection, let me call it D, on the spinor bundle. And this connection, let me just write it down once, although it appear again later, but let me just say, the connection is going to be the spin connection, and then a correction, which is a one-form with values and endomorphisms of the spinor bundle. So in some conventions, it's going to be 1/24th. I'm going to confuse one-forms and vector fields, so if you don't mind. So I'll just have X, Clifford product F, Clifford product, minus 3, the other way around, F. Anyway, so this connection actually has all the information necessary to discuss bosonic backgrounds of the theory, i.e. solutions of the field equations where the gravitino has been set to 0, and in particular the ones that preserve some supersymmetry. So, so let me mention two things. So the things that, because I'm running out, I'm not sure, let me try something. So can you see both pages? No? Okay. That's going to be a bit strange.
Is it just side by side?
You can see that. But then if I zoom, you see the zoom. or not? You don't see the zoom. Oh, very good. Okay. So if you don't mind, I can do it like that. Okay. So so from this this connection, I get the following data. So first of all, we define the notion of killing spinner as the parallel spinners. So killing spinners is just the kernel of D. Of course, this the rank of this bundle is 32, so this space is dimension at most 32. So so dimension of curve D, it's a vector space, it's a linear operator, so dimension of the kernel is going to be, well, it could be anywhere between 0 and 32. But the other interesting thing about this connection is that if you were to compute the curvature, let's say RD, so the curvature of this connection, and you look at the so-called gamma trace. So what is this? This is a one form with values in endomorphisms of the spinor bundle. This being identically 0 is equivalent to the following three things. First of all, the fact that df is 0. In order to define D, you don't need to actually impose that it be closed. So it follows from one of the components of this. But the other ones are the two other equations, the so-called sort of Maxwell-like equation, which is something like D star F in some conventions, 1/2 F which F. And of course the Einstein equation, which I'm not going to write down. So precisely the equations of the field equations for bosonic backgrounds of the theory are encoded in this in this connection. Okay. So what do we know about this connection? Well, Chris proved many years ago that the holonomy is actually quite generic. So I forgot when this was. 02, 03, something like that. Something like that. Okay, let me say 02. 3, maybe, I don't know. Anyway, so so the restricted holonomy of D is actually SL32R. So the only thing that it preserves generically is a volume form on the spinor representation. So actually, Mike Duff et al. So probably around the same time, studied many of the examples for the known solutions at the time, studied what the holonomy looked like. So let's say hol D for many backgrounds. So huge lists of possible holonomy groups. But I think it's fair to say that we don't have anywhere near a holonomy classification like you would have for perhaps torsion-free connections on the tangent bundle or something like that. I mean, this is much more complicated. So although it'd be interesting to maybe understand the holonomy of this connection at this moment, it's safe to say that not much is known except for examples. Okay. So what else do we know about this? So the title of the talk is Lie superalgebra deformation. So what are the Lie superalgebras? Well, it turns out that every such background has an associated Lie superalgebra. So this is a so-called killing superalgebra. So this is, okay, let me call it K0 plus K1. So K1 is just the killing spinner. So this is just the sections of the spinor bundle which are parallel. And K0 is going to be all the vector fields which preserve both the metric and the four-form. So it turns out that on this two-graded vector space, I can define the structure of a Lie superalgebra. I'm not going to tell you what the brackets are, but it's kind of the obvious one. I mean, K0 is just Lie bracket of vector fields. K0 and K1 is the Lie derivative of the spinorial Lie derivative. And K1 going to K0 is precisely this Dirac current construction. Okay, so the nice thing about this Dirac current construction is the following. It's a purely linear algebraic fact. So remember that we had this. Let me think of it now as a linear map from, it's bilinear, so, and symmetric, so from, that's my notation for symmetric square, to V. And this induces a map, let me also call it kappa if you want, from sections of the symmetric square of the spinor bundle to vector fields. And the nice thing about this is, first of all, that when the spinors are in the kernel of D, the resulting vector happens to preserve both the metric and the four form. But the linear algebraic fact that I was referring to is that if I have some subspace of the spinor representation whose dimension is greater than 16, which is half the dimension of S, then if I restrict kappa to S prime, this map is surjective. And therefore, it follows from that if I have a supergravity background such that the dimension of the space of Killing spinors is greater than 16, so so-called greater than 1/2 BPS background, MGF, then, well, every point in the tangent, at every point, the tangent space is spanned by vector fields that preserve the metric and F. And basically what this is saying is that the background is locally homogeneous. This was conjectured by Patrick Mason back in 2004, and we tried to prove it at the time, but we didn't succeed due to a kind of oversight. But then I proved it together with my student Noel Hostler in 2012. So that's, in some sense, it's quite useful in the sense that well, as you know, solving PDEs that are, in geometric PDEs, homogeneous geometry, when all the data involving in the PDE is homogeneous, actually becomes an algebraic equation. So in order to find homogeneous backgrounds, you don't have to solve PDEs, you have to solve algebraic equations. Doesn't mean they're easy to solve. I mean, some of these algebraic equations, as you can imagine, they're quite complicated, but the point is substantially simpler than solving the PDEs. Okay. So let me tell you what's known about this. Sort of the state of the state of art. Only about greater than 1/2 BPS backgrounds. So I want to make a little table. So let's say dimension kernel of D. And is that visible? Yeah, hopefully. Okay. Sorry. So let's see. So let me write down. So 32, go down 31, 30, 29, 28, 27. Am I going to run out of space? Probably. Sorry. So 19, 18, 17. Okay, so what's known? So let me tell you just briefly. So this is completely known. We classified all the ones with 32. It is known that there's nothing in 31 and there's nothing in 30. That has been determined. We've no idea, meaning there are no examples, but also no proof that none exist in 29, 28, and 27. There's a PP wave that was discovered by Michelson in 26, but so there exists something, so, but we don't have a classification. Nothing about 25. 24, there exists, there's PP wave, and there's a kind of a Freund-Rubin background. 23, that was 24. I skipped one when I moved the cursor. 23, we don't know. 22, there's some PP waves. 21, we don't know. 22, there's PP wave, and there's a Gödel solution. 19, we don't know. 18, there's a PP wave, and 17, we don't know. So that's the state of the art, which is fairly depressing given that it's been going on for so long, and basically what we have is a number of constructions. Most of the PP waves are work of Jerome Gauntlet with Chris. Gödel is the uplift of the 5-dimensional Gödel. The Freund-Rubin, it was there all the time, but people didn't notice. And the 32 is, of course, the Freund-Rubin backgrounds, the Kowalski-Glickman PP wave, and of course, Minkowski space-time. And the non-existence results here, these are work of Gran, Gutowski, and Papadopoulos. The 31, they did it only locally, and then with my student Sunil Gadia, we proved that we couldn't get them by quotients either. The 30, they did everything themselves. So anyway, that's kind of the state of the art. There's one thing here that is clear, is that there seems to be a supersymmetry gap from the maximally supersymmetric to, well, the first one that we know is 26. So it could be that the gap is, from 32 to 26, but of course there could be something, those question marks in 29, 28, 27, it means that we don't even know what the gap is. And this is to be contrasted, by the way, with the gap in, say, Riemannian geometry or conformal geometry, or generally there's a gap phenomenon in Cartan geometries, where if you're looking at the automorphism, the dimension of the automorphism group of some geometrical structure, there's some structures that are maximally symmetric, and then there's usually a gap for the second one, right? Like, for example, in isometries of a Riemannian manifold, we know that, if the manifold is n-dimensional, maximally supersymmetric has a dimension n+1/2 automorphisms. And you might think, well, is there anything which has automorphisms n+1/2 minus 1? It turns out no, that there is a gap. So similarly, there's clearly here a gap phenomenon, at least for the dimension of the odd subspace of this superalgebra, and we don't even know what the gap is. So that's one obvious question: what is the gap? How big is it? And of course, the overriding problem here is perhaps the classification problem of these backgrounds, perhaps up to local isometry. So there are a number of standard approaches that people have followed. The tried and tested approach is explicit construction by ansatz. So you write down some ansatz based on some symmetries. You try to find the solutions. Then there's other approaches having to do the so-called G-structure approach, the spinorial geometry approach. But it's fair to say that basically all these approaches can kind of hit a wall. At some point, you cannot make further progress. So we started kind of looking at other ways of doing it. And the approach that I want to mention in this talk is this one based on deformation theory of Lie superalgebras. So you might wonder why this approach even exists. So actually, the origin of this work has to do with this conference in Adelaide that Matai invited me to. And there was a talk there by Dennis Tay, where he was talking about the gap phenomenon in Cartan geometries. And this resonated quite a lot because it just seemed to me very similar to the supersymmetry gap in this classification of supergravity backgrounds. So when I went back to Edinburgh, Andrea Santi was postdoc there on a Marie Curie fellowship, and I mentioned this talk of Dennis. And Andrea had been thinking about this problem from some work he's interested in, sort of Tanaka structures on supermanifolds, which is a theory that doesn't quite exist yet, but is something he's been trying to construct. So he suggested that we should try to pretend that such a theory existed and do the kind of calculations that such a theory would suggest. And okay, it's a long story, and we didn't get. I mean, it wasn't a direct path. It was kind of a very circuitous route until we actually got to this thing. But let me mention the fact. So it's a theorem that Andrea and I proved. So let me just state it as a fact. I'm not going to prove the theorem here. Is that this Lie superalgebra associated to supersymmetric backgrounds, the Killing superalgebra, is actually filtered. So the Killing superalgebra, let me call it K, is actually filtered. So what does that mean? It means that, okay, so the filtration goes up. So let me write the superscripts for filtration and subscripts for gradings. So there's going to be filtration level -2, then -1, then 0, and then like that. And filter just means that if you take something in filtration level I and you take the bracket with filtration level j, this goes into filtration I plus j. Okay. Every time you have a filtered object, there's an associated graded object. So I can think of the associated graded object of K. So this is going to have something in degree -2, something in degree -1, and something in degree 0. So what are these things? So this is basically, well, this is everything filtration degree -2 modulo the things in -1. This is -1 mod 0. And this is just 0 because there's nothing in positive degree. So we can call these things something. Let me give them names. So this is going to be V prime. This is going to be S prime. This is going to be H. So where do these live? So V prime is some subspace of the vector representation, right? It's the thing that is sitting in degree -2. This guy's inside the spinor representation, and this guy's inside SOV. Now, because of the fact that K is filtered and degree 0 is H, H is a subalgebra. So this is actually subalgebra. The other ones are subspaces. And this linear algebraic fact that I pointed out before is that if the dimension of S prime is greater than 16, then V prime is actually V. Okay. Sorry, so when?
We started at the 9:45, so we still have 35 minutes.
Okay, all right, just wanted to, thanks. Okay, so anyway, so it's filtered, and whenever you have a filtered Lie algebra, the associated graded is a graded Lie algebra. And the result is that this is actually this V prime plus S prime plus H. This is a graded, Z-graded Lie subalgebra or sub-superalgebra of the Poincaré algebra. So, so this guy is a Z-graded Lie sub, let me just say sub, even though it's sub-super, whatever, Lie superalgebra of Poincaré. So one thing you could say is that the Killing superalgebra of a supersymmetric background is filtered. The associated graded is a subalgebra of Poincaré. So one way of saying this is that the Killing superalgebra is a filtered deformation of a subalgebra of the Poincaré superalgebra. So what does that mean? So that means that basically you take the subalgebra of Poincaré with data V prime, S prime, and H, and then the Killing superalgebra is going to be adding the terms of positive filtration degree to those brackets. So let me try to make this precise by writing some. So here I'm going to let capital A and B be elements of H, and remember that this is a subalgebra of SOV, so these are skew-symmetric endomorphisms of V. Let VW live in V, and let S, the bracket is symmetric, so I don't have to take S1, S2, I can just take one of them, B prime, and this is S prime. And the brackets are going to be the following. So, yeah, I have room to write them here. So A and B, of course, is the standard commutator of endomorphisms. A acting on V is just, A is an SOV, so acts on V. And A acting on S, well, it's the spinor representation, we call it sigma of A acting on S. Right now what I'm writing is subalgebra of Poincaré superalgebra. So the other possible brackets are, well, I could take S with S. It's symmetric, so it's enough to know what it is on S. And this is the Dirac current. V with S would be 0, and V with W would be 0. So this is what it happens in the case of subalgebra of Poincaré. But this is now a filter deformation, so it means I add terms of positive degree. Now, this one I cannot change because I have nothing in positive degree in the algebra. So this is something which is degree 0 goes to degree 0. Positive degree means that it would have to give me an element in degree greater than 0, but there isn't. The only degrees that I have are 0, -1, and -2. So that's fixed. Similarly, this one here is fixed because I want it to be a Lie superalgebra. So the degree is always going to be even because the parity is the mod 2 reduction of the degree. So there's nothing in degree 1, which would be the thing that I could add here. But I could add, for example, something, let's say, let me call it delta VV, which is something of degree 0. So A is degree 0, V is degree -2, AV is degree -2, and then I have something which is degree 0. So this guy is in SOV. Similarly, these guys I could try to deform by adding things of positive degree. So for example, let me do it in a different color. So here I have, let's say, gamma SS. So this is something of degree 2, which lives, well, S that has degree -2, degree 2 is degree 0, so this is in SOV. This one, let me call it V of VS, and here I have two possibilities. I have something which lands in V and something which lands in SOV. So let me, next to it, say maybe I can write down the degree. So this thing here has degree 2, degree 2, degree 2, degree 2, and this one here has degree 4. So in principle, that's the most general, filter deformation that I could write of a Z-graded subalgebra of Poincaré. And, all I have to do is, if you want, write the most general thing and impose Jacobi identities. That's not how we're going to do it. That's a lot of work. So the thing to notice is that just like for deformation theory of Lie algebras or Lie superalgebras, there is a cohomology theory that governs these deformations. There's going to be some cohomology group in some cohomology theory that classifies the infinitesimal deformations, and then there's a group of higher degree that classifies the obstructions to integrating the deformations. So what this theory is in this case, it's a refinement of Chevalier-Eilenberg cohomology, something called generalized Spencer cohomology. And in this version, it was something that was introduced by Cheng and Katz in the late 90s, in 98. So let me try to describe it very quickly. It's really Chevalier-Eilenberg with refined by degree. So in this, rather than doing the general case, let me just look at the case that one case that I'm interested in. So let me, suppose I'm looking at Poincaré. So remember, Poincaré is graded and has P0, P-1, P-2, which is, SOV, S, and V. And let me call P-1, P-2, that forms, because it's graded, that forms a subalgebra, and I'm going to call that P-. It's the negative graded part of the... And then what I can do is, well, P- is a Lie superalgebra, and it's a subalgebra of P. So I can take the adjoint representation of P on itself, restricted to P-. So P becomes a P- module. So that means that I can construct and I can define sort of Chevalier-Eilenberg complex. So let me call it C of P minus, the Lie superalgebra P minus with values in the module P. But now the nice thing about this is that because this algebra is graded, the Lie bracket has degree 0. That's what it means for a Lie algebra to be graded. It means that the degree of the bracket is 0. And the differential in Chevalier-Allenberg is essentially the dual map to the bracket. So the Chevalier-Allenberg differential also has degree 0. So it means that I can refine this complex and break it up by degree, and the differential will preserve the degree. So actually, this becomes a direct sum by degree of something which I'm going to call D here. So this is the degree. So the degree here is 0, -1, -2, as the label suggests. Anyway, so the point is that I can refine this, and I can calculate cohomology degree by degree. So, so the cohomology of this complex, of each of the degree pieces, this is what's typically known as, this is called generalized Spencer cohomology. Generalized Spencer complex. And this is Cheng and Katz, 98. Okay, so so what Cheng and Katz showed is that HD2, this essentially controls infinitesimal deformations, infinitesimal filter deformations. So provided the degree is positive, infinitesimal. So let me say D greater than 0, infinitesimal filtered deformations. And HD, 3 has the obstructions to integrating that, but usually there's no need to calculate that. Okay, so let me give you an example. Let's take P to be our favorite 11-dimensional Poincare superalgebra, and let me tell you one calculation. So let's take D equals to 2. So I want positive degree, but it has to be even because I want to preserve the parity. So D is equal to 2. And let me compute H22. So what is that? Okay, I'm not going to do the calculation for you, but I'm going to at least give you an idea what this complex looks like and then tell you what the answer is. So what do we have? So let me write C. Let me not write P minus P all the time. So let me just write C12, C22, C. Sorry, I'm doing it the other way around. I meant degree is always 2. So 2, 1, 2, 2, 2, 3. So I'm looking at that. So let me write these things down. So remember, these are skew symmetric. Well, this would be a map from P minus to P of degree 2. So basically, the only thing I have is in P I have degrees 0, -1, -2. So the only thing that has degree 2 is mapping the degree -2 thing to the degree 0. So this thing here is this space is going to be hom of V SOV. Now, the Chevalier-Allenberg maps to C22. Okay, so C22 are things which are bilinear, skew symmetric in the supersense, and degree 2. So it turns out there's 3 components to this. So first of all, I have hom lambda 2VV. Right, that clearly has this skew symmetric, bilinear, degree 2. Then I also have hom V tensor SS. And finally, I have Hom symmetric square because it's skew in the super sense, and this is odd, so symmetric square SOV. And what do I have? What do I have in 2.3? I have, well, these are trilinear things, so I can have symmetric square S tensor V mapping into V, and I could also have symmetric cubed on S mapping into S. Anyway, that's a complex, right? And I just point out, let me point out two facts about this complex. The first of all is that this first D, this is actually injective. So there's no kernel to D there. Moreover, if I look, if I map and I project to the first, if I just project to this first guy here, D is an isomorphism. So D projected from Hom VSOV to Hom lambda 2VV, this is actually an isomorphism. And by the way, these maps are always SOV equivariant. So everything is kind of Lorentz equivariant. Okay. So what that means is that if I want to, remember, I'm interested in H22, so I'm actually interested in the kernel of this map here, modulo the image of this one. But I've just shown that this is injective, and moreover, this guy here is an isomorphism. So that means that any cocycle in here, anything which is scaled by delta, there's going to be, in its cohomology class, there's going to be precisely one cocycle who has no component in Hom, you know, whatever cocycle I have, it will have a component in Hom lambda 2VV, and I can basically by adding a coboundary just get rid of it. So if you wish, perhaps I'm getting into more details of the calculation than I wanted to, but just to point out. So so H22, this is actually going to be the kernel, right? I don't need to, I can normalize the cocycle, and therefore I don't have to divide by anything. So it's just going to be, strictly speaking, the kernel of D mapping Hom V tensor S to S plus Hom O to S SOV into whatever, into C23. So let me give names to the different components of the cocycle. So this one I call alpha, this is called beta, and this is called gamma. And I should remind you that this alpha, beta, gamma are precisely this alpha, beta, gamma here. So these are exactly those maps, it turns out. Anyway, right. So so let me tell you the answer. So when you do this calculation, you find that H22, this is isomorphic as SOV modules to lambda 4V. So are the four forms, so to speak. And then we can ask, well, I've normalized the cocycle so that alpha is 0. So what are beta and gamma? Well, I'm not going to tell you what gamma is. It's just given in terms of beta. But let me tell you what beta is. So suppose that I have, let me call phi the fourth form that is labeling this cohomology class. Then it turns out that beta corresponding to phi, so remember beta takes a vector and a spinner and gives me a spinner. So what is that? Well, hope you recognize this. So this is 1/24th V Clifford product with phi Clifford product. Well, don't need to write Clifford product there. Minus 3 phi V S. So what is that? Well, if you remember, this was the correction to the spin connection that appears in the 11-dimensional supergravity variation of the gravitino. So this is the, so I had it early on. This is this. Different notation because, okay, this is you know, X vector field F4 form, but it's basically this bit here, the 1/24th, that is exactly the expression of the cocycle, for the beta component of the cocycle. Okay, so you might think, well, you know, suppose you don't normalize the cocycle. Suppose you actually consider the cohomology class with perhaps you know, what happens if you add alpha? So if you add alpha, all that happens is that you're adding, it's like adding torsion to the spin connection while keeping it a metric connection. So all I'm trying to say is that if you were to choose a different cocycle representative for the same cohomology class, instead of modifying the spin connection, I could modify another metric connection with torsion in such a way that that connection minus the beta that you just give me is exactly the same killing spinor equation as in 11-dimensional supergravity. So the freedom is just the freedom of which connection I start to derive. Okay, anyway, so that's interesting. That's in some sense, I mean, when we did this calculation, this is what convinced me that we were onto something, just because somehow a priori there was no reason to expect that what this is doing is it's trying to look at constructing infinitesimal filter deformations of subalgebras of Poincaré, and there was no reason to expect that maybe the only way to do that would be the killing superalgebras of supergravity backgrounds. But in a way, what this is telling you is that this seems to be the natural thing. Okay, so after 10 minutes, more or less?
14 minutes.
Oh, okay, right. So let me tell you then, right, so that's just the result of the calculation. Then let me tell you a couple of other results that I've obtained with Andrea along these lines. And one is the reconstruction theorem for supergravity backgrounds that are greater than half BPS. So the idea is that in some sense, the killing superalgebra has enough information to reconstruct the background. So if you give me any filter with, I mean, the theorem is long, so I'm not going to tell you exactly the theorem, but okay, so let me at least give you the gist of it. So this is the sort of reconstruction. Okay, so suppose I have, suppose K is a filtered Lie superalgebra, and suppose that the associated graded is subalgebra of Poincaré. So it's Z graded subalgebra of Poincaré. And let me assume that the dimension of S prime, which is the subspace of S in here, is greater than 16, and that means that V prime is actually V. So as a vector space, or actually as a subalgebra of Poincaré, this guy looks like what? It looks like, well, some subalgebra of SOV, some subspace, but then here you have all of V because S prime is sufficiently large. And H is a subalgebra of SOV. Okay. So maybe just to be honest, I write down the conditions. So the reconstruction theorem says the following. If there exists some map from V to SOV such that the following conditions are satisfied. So remember that, let me go back to, so I have these, alpha, beta, gamma, delta, and rho. I call rho because actually that's a curvature. So alpha, beta, gamma, delta. Okay, so there's some conditions that need to be satisfied. If there is a map from V to SOV such that the following conditions are satisfied. So first of all, alpha VW is just a coboundary by that map, right? So that's a map in, where is it? In C2. This is the map here in C21, homomorphisms from V to SOV. So if there is, so this one is just saying that this is XVW minus XWV. Beta VS to be the one that I get from this phi is going to be the 4 form. This is a spin representation on XV acting on S. Gamma SS is the one I didn't write, but that you get from the calculation, minus X applied to the Dirac current. And delta AV to be the bracket of XAV minus X of AV. And so if there exists an X such that these guys take that form, where phi is some element in lambda 4, and it satisfies an algebraic condition, which is equivalent to saying that the corresponding 4 form is closed, but you can write that algebraically, then K is the Killing superalgebra of a greater than half BPS sugra background, determined up to localized symmetry. So we cannot do better than that. Okay, so so that's sort of a reconstruction theorem. And the important thing about this is, when I say background, it means that it implies the equations of motion. So this is not just, you know, so provided that that these solutions are, these equations are satisfied for some. So the data here is the X and the 4 form being closed. Then you can reconstruct up to localized symmetry a solution of the equations of 11 dimensional supergravity, preserving more than half the supersymmetry. That's the statement. So then the question is, well, that seems like a kind of complicated set of equations. So what is the smallest data that would allow you to kind of reconstruct this? So yeah, let me tell you the story. So this is going to get a bit technical, but okay, just to tell you the. So what is let's say, what is the smallest data specifying the background, or specifying K, which is the same thing by the reconstruction. Well, okay, so so let me consider S sitting inside S prime, and let me consider the Dirac current restricted to, so we know this is surjective because S has sufficiently high dimension. Let me define D like this, the kernel of this map. So we have an exact sequence like this. So this is something that we like to call the Dirac kernel, just because, sorry, I know Dirac kernel in index theory means something else, but here it just means the kernel of the Dirac current. Let me erase this because I want to put some arrows down. Okay, so I have a map, which is this map that we call gamma phi, that maps this to SOV. And then we have, we can restrict that map to the kernel of no, this is the restriction. This is gamma phi restricted to D. And this is something that we like to call the envelope of, well, okay, so let me define the pair S prime phi, which is, in some sense, what we're going to show is that this is the basic data that we need. We call this a Lie pair if 2 properties are satisfied. If for all A in this so AS belongs to S prime for all S in S prime, and if A phi is 0. And then what you can show is that if S prime phi is a Lie pair, then this thing here is actually a subalgebra. So it follows from here that H of S prime phi is actually a subalgebra of SOV. And in fact, it's not just any subalgebra, that's the subalgebra H that appears in the, so it follows from this, you have to show it, but that H of S prime phi together with S prime together with V is a Z-graded subalgebra of Poincare. So this is the thing that the Killing superalgebra is deforming. Okay, so so we have a, okay, I think I have time to say it. We have a, yeah, okay. We have a refined version of the reconstruction theorem. So this is reconstruction version 2. So now, instead of looking at the Killing superalgebra, I can look at the ideal generated by the Killing spinors. So if you have any superalgebra, for example, we have this Killing superalgebra, K0 plus K1. Inside here, I can look at there's an ideal of K0, which is just the things that I get by brackets of K1. So I have something which is K1, K1, and K1. So this goes by different names. I like to call it, if this is the Killing superalgebra, I like to call this the Killing ideal. Or Andrea likes to call it the transvection superalgebra because he's now getting into this algebraic group stuff. But anyways, transvection superalgebra of the background. So the reconstruction version 2 is, well, basically is that the Killing ideal is enough to reconstruct the background. You don't need the whole symmetry. So the difference between these two things, for example, in Minkowski spacetime, the transvection superalgebra is just going to be translations and supercharges, whereas we know that, of course, the Lorentz transformations are also symmetries. So the Killing superalgebra is bigger, but it's enough to reconstruct it if you just give me the translation, the super translations, right? I mean, that's enough to reconstruct Minkowski spacetime. Well, in general, the Killing ideal is enough to reconstruct the so basically what we have now is the following result that says that so the Killing ideal of a greater than 1/2 BPS sugra background is a filter deformation of, well, of the thing that I wrote before, H of S prime phi plus S prime plus V, where S prime phi is a Lie pair. And the map X, remember we had a map from V to SOV. Well, this map is actually going to be, so X is going to be X phi precomposed with some section of, remember that we had this exact sequence. So, and then what I do is you choose any vector space section here, sigma, and you compose that with gamma phi, or the restriction to gamma phi to that, and this going into SLV, and this map, this is X. Okay. And Andrea has recently, I'm not going to write down now, so I don't have time, but he has recently simplified a little bit the, these equations in the original reconstruction theorem of what they had to be satisfied. And basically, it's down to two slightly different equations that need to be satisfied by the Lie pair, by S prime and phi. And then the pair S prime phi subject to two relations is enough to reconstruct the background. That's something he did very recently, December of last year. So I won't write it down. The equation is long, but anyway. So the question is, what does this buy you, right? So we have a different approach. If we go back to what was known, or rather not known, so this approach. With this approach, we basically managed to reconstruct, to reprove this bit, only the 32 and 31. The reason is because finding these Lie pairs is not such an easy proposition. Finding, it's very difficult to dial your favorite fraction of supersymmetry and find a subalgebra of Poincaré, which precisely has that dimension for S prime. But with sufficiently high supersymmetry, we've managed to somehow, by using some representation theory, actually, write down. So for dimensions 32 and 31, that can be done. That approach is not going to work for lower. But okay, so we're still thinking about, in any way, in a way, the way I would like to solve this is by saying we have a complete representation theoretic reformulation of the classification problem with a set of other questions that need to be answered in order to obtain the classification. And there are some tools that perhaps can be developed to answer them. Okay, I'll finish there.
Questions for Jose?
I somehow missed the logical step from the Spencer cohomology to the reconstruction theorem. Was there a systematic way of going there, or did you?
No, the Spencer cohomology was essentially that calculation I presented just to convince you that this has something to do with 11-dimensional supergravity. And the reason why is because of the fact that the killing superalgebra is a filter deformation, and that's what the generalized Spencer cohomology is calculating. Now, in order to, once you give, the way the reconstruction theorem works is if you give me already a filter deformation, and in a way, the way the Spencer calculation works by, I showed the Spencer calculation for the whole Poincaré algebra, P minus P, but actually what you would like to do is for the actual subalgebra of Poincaré that you want to deform, right? The infinitesimal, so the Spencer cocycle condition corresponds to several components of the Jacobi identity of the full thing already. So we use it as a kind of a bootstrap in order to already solve some of the Jacobi identities and then look at the other ones. But the way the reconstruction works is really, two things. So if you give me already the filtered deformation, so if you give me the filtered algebra with a dimension of S prime greater than 16, we know from this linear algebra fact that this is going to be homogeneous, and you can just reconstruct the homogeneous space. And then you reconstruct, it has an invariant four-form, invariant metric, and then you need to make sure that the equations of motion are satisfied. And that's really, in some sense, the heart of the reconstruction theorem is to ensure that the Jacobi identities of the killing superalgebra actually imply the equations of motion. So that's I didn't show it here. I mean, that's what's inside this reconstruction theorem. It's just basically reconstructing up to local isometry a homogeneous space from the infinitesimal data. In this case, actually, you can think of it as a homogeneous superspace, actually. But in any case, a homogeneous space with infinitesimal data out of the infinitesimal data, and then checking that the invariant objects that you have, namely the metric and the four form, satisfy the field equations of supergravity. And that just follows by application of the Jacobi identities of the Killing superalgebra. Of the thing that you hope is a Killing superalgebra, and then you show that it is indeed the Killing superalgebra of that background.
Other questions? Chris?
So what happens if you try and extend this to 16 supersymmetries? And can you see why there's so many more solutions which come out?
Well, the thing is that we don't have a reconstruction theorem for 16 because they don't have to be homogeneous. So this theorem of homogeneity is sharp, right? I mean, the M2, the M5, they're cohomogeneity one solutions. So you don't reconstruct it. There's always some additional function of if it's cohomogeneity one, there's an additional function that cannot be fixed from the symmetries. So what I mean is there's dependence in an additional coordinate that cannot be fixed from the symmetries. So there's no reconstruction. I would say that the one naive reason why there are so many more half BPS solutions than greater than half is precisely that, the fact that you're not constrained by homogeneity. And, symmetries or supersymmetries constrain the form of the solution. The more you have, the more constrained they are. And it just happens that half BPS is precisely the threshold of homogeneity. Be 16 or less doesn't have to be homogeneous. 16 or greater than 16 has to be. And I think that's kind of the reason.
Other questions? I have a quick question. So the cocycle beta that you got has the exact same form as you indicated as a correction to the covariant derivative with the numerical factors, relative and overall.
Well, the numerical factors is a choice. We chose it so that, because it's a question of, well, yeah, in the sense that it's a four form that we get, and we could call that four form 3 times phi rather than phi, and you would get another form. So we chose it for maximum effect, just so that it looks the same. But there is a question of how do you relate the four form F in the supergravity and this cohomology class. The representations are isomorphic, but that just means that you could, you could rescale. It's a linear isomorphism. I mean, it doesn't have to be the identity. It could be some factor times the identity.
Great. Let's thank Jose again. Oh, sorry, one more question. William?
I was just wondering, so how does everything change if you change the section, the sigma?
Changing sigma essentially adds something in the kernel, right, in D. And remember that D maps to H. So essentially, you're just re-embedding V in a different way in the deformation, but there's no actual change.
Other questions? If not, let's thank Jose again.